So on Twitter, we have a question from Jacob Hill, and he says the population of a country increased by an average of 2% per year from 2000 to 2013. Oh, yeah.
Oh, I guess it continues on the one above.
Yeah. If the population of this country was 2 million people on December 31st, 2013, then what would the population of this country be on January 1st, 2000 to the nearest 1,000?
I'm going to need those numbers again. I can't see them at all. Are you able to see them?
Yeah, let me see if I can pull them up.
I've got it right here, too. So we're going from the year 2000 to 2003. Is the range.
Am I doing this one, or are you doing this one, Nathan?
You can go either way. You already got it started, so.
Not much. You go for it. It's
All right.
yours.
All right, Nate.
What do we got?
Here's 2000 to 2003.
So from 2000 to 2003.
And at the end of 2003, so December 31st of 2003, the population is 2 million.
So we're talking about the beginning of 2000?
Yeah, the beginning of January 1st, 2000.
Okay, to the end
to
of
December
20,
31st, 2003. 2 million people on December 31st, 2003.
2 million.
And over this period, the population of the country increased by an average of 2% per year. So the question is, to the nearest 1,000, can you give us the population on January 1st, 2000?
So this is an exponential question. So what we need to first talk about is the form of an exponential equation. So I typically write it as y equals a times b to the power of x. And talking about what these components mean really helps. So if you feel like you're just sometimes lost in these exponential, I would always think about what these components mean. So y, think about y as like your final amount, in which case a is going to be your starting amount, like your initials. So in this case, my first thought is I know my final amount. I know that at the end of 2003, there were 2 million people, right? It's population. And then we need to think about the growth rate, B here.
And Nate, can I just make a note on that?
Sure.
I think it increased by 2%. Just
Oh, not
2%.
2.3, okay.
Yeah, sorry, I think I might have mumbled that.
Yeah, I was
did
like,
I
wow,
write-
this is a really specific question.
Yeah, no,
I-
2%. 2% per year.
Okay.
I somehow wrote down or heard 2.3 for some reason.
Yeah.
That must have been me.
Okay, so let's change that to 2%. And then this is going to be your growth rate. Let me do that in the different colors. It's not confusing. Growth rate. And then this x up here is going to be time. So we can think about this a couple ways. One is I don't really like, and Becca, maybe you can chime in if this is something you do or not. When I have these really big numbers, like 2 million, like a nice, even, really big number, I usually just go with 2. Is that something you do, or do you just go 2 million?
I usually do too.
Okay.
Yeah.
So in the end, we're going to say, I'm going to convert this to 2 million, because as you're working through these math problems, sometimes we have these really ugly, like big numbers that make it challenging on a calculator even. So I like to just make an easier number to work with.
And we know that whatever our solution is or whatever our answer is going to be in millions.
In millions,
Just
yeah.
like we're reporting this to. We're saying it's
Right.
2 million.
Right.
You know, million is almost the label now.
Yeah. So when we get our final answer, we're probably going to, I'm going to guess we're going to have some crazy decimal, and we're going to end up just multiplying it by 1 million, or saying whatever million. So all I'm going to do now is think about like this equation that I have here, and I'm going to say, well, do I know the final amount? And actually, let me take a step back really quick. Again, I like to read these problems and really think about what's being asked, and we're really trying to figure out how many people were there in the beginning of 2000. So I'm looking for this initial amount, which means if this is what I'm looking for, I have to know every other component of this. So I'm going to walk through this now and think about like what information I have. Do I know the final amount? Yeah, I know at the end of 2003 we had 2 million people. So I'm going to write this over here, and I'm going to say 2 equals A. I don't know what the A is, because that's what we're looking for. And now B is a growth rate, and this is kind of a tricky, I don't want to just say it's 1.02, but think about like if something grows by 2%, if you want to figure out what percentage it grew or the amount that it was increased by, you would just do that number times 0.02. You convert it to a decimal. But we also have to consider that we still have our initial amount. So it's going to be 1 plus that. And I'm not going to get too into that. I'm going to assume that that's something that you know, because that'll take an extra 5 minutes. So we're going to do times 1.02 to the power of x. And this one, I think they did this on purpose, a little tricky.
Well, it's not to the
Beginning of
power
2000.
Oh,
I'm gonna-
I see
I'm
what you're
gonna put that
saying.
in.
I see what you're saying.
So,
Sorry.
Yeah, I'm looking for x right now. I'm thinking about what it is. Beginning of 2000 to the end of 2003, my first thought might be, oh, it's 3 years, right?
Mm-hmm.
But we said the beginning of 2000s, we have all of 2000 is 1 year. We have all of 2001 is 2 years.
Mm-hmm.
All of 2002, we have all of 2003. So we're actually talking about 4 years. So I'm going to put a 4 up here. So you got to be really careful about that because we said beginning of January to end of December and just think that through.
Mm-hmm.
Now, from here, we're just going to solve. And so, Becca, if you could help me out with the calculator. So 2 equals, and all I'm doing is simplifying this side of the equation. We don't really like to have exponents when we don't have to have them in this case. So Becca did this on the calculator. 1.02 to the power of 4 right here is going to be this kind of big number here, 1.082432216. Now we have basically a simple equation to solve. 2 equals a times some number. So we're going to divide it by that number. And I want to kind of point out one thing here is that I don't want to keep rewriting this entire thing. But in a calculator, you'll see, you probably can't see this, but it's kind of a long number. And you don't want to like leave stuff out if you want to be more precise. So we end up just doing the answer. So, but I am going to divide it by this on both sides. I probably should have just rounded it. And we're going to get a equals, let's see, 2 divided by that answer, 1.847.
Yeah, use that answer button in your calculator to do the calculations because it helps you keep it accurate, as Nathan was saying. Don't round it if you don't have to. Use that answer button.
Yeah. So we have 1.8476908, and that number continues a little bit further. But remember, we wanted to know how many people to the nearest, what, thousands?
Millions.
Nearest thousand.
Nearest thousand.
Nearest
Okay.
thousand.
Was we wanted the answer.
So what I'm going to do with this number is I'm just going to multiply this by 1,000,000. And I get, and I'll write this down so it's clear. I multiplied this number by 1,000,000 in my calculator. And you're going to get A equals 1,847,690. And we wanted to round it to the nearest thousands. So we can actually round it to 1,848,000 people approximately. So these problems can seem a little tricky, but if you just try to think about what you know and really like don't just try to memorize this equation and plug stuff in, think about what all of it means and how it relates to each other. That'll help you kind of think about like what information you have and what information you're looking for and solving from there.
And I think also one of the confusing parts about these types of problems is what kind of equation do I write?
Right.
You know, and if you can understand that, oh, well, when something's growing by 1% or decreasing by 1%, that's always an exponential relationship, then you then know what kind of equation you have and fill in our parts.
Right.
So thinking about the relationship between the numbers as well.
Okay.
So what do we
This
I'll
one
take
is
any of those.
From Jonathan, and he says, what's the difference between a linear equation and a nonlinear equation?
Okay, I got it. A linear equation, what makes an equation linear, first off, is the shape that it creates when we graph it. For example, a linear equation is going to almost always, or not almost always, it's going to always, not almost, always create a line, no matter what. When we're writing a linear equation, and I'm going to give an example of it. What makes it linear is the degree of the equation. And the way that we talk about the degree is by the highest power that is on our variable. And what you can kind of see here is that there's no power written on there. So really, it's a first degree equation, and that's what makes it linear. Anything else that is not first degree would not be a linear equation. For example, if I had something like this, 3x squared plus 2, that would be a nonlinear equation. So definition of linear is, first off, that it creates a line when you graph it, and then second, that it's a first degree equation rather than a second degree or something like that. I think that answers it. I think it covers it.
Straight up.
Yeah, and I think the interesting thing about that is like thinking about what happens like when we have a linear equation, changes by the same amount every time. Whereas like nonlinear, typically it's changing because your value before is changing.
You're right. That's a completely defined characteristic of linear equations is the fact that there is constant growth.
Right.